All right, this is a fun one. We're going to take a BJT amplifier with a known frequency response, FC high, and we're going to do some emitter peaking, which is going to improve our FC high and extend our bandwidth. So here's our common emitter amplifier using universal biasing. And in the previous videos, we've looked at how to calculate the low frequency cutoff and the high frequency cutoff. So here's our AC redraw at high frequencies, and we can see we've got our C total in and our C total out. And this is how we calculated that final FC high cutoff frequency. So let's back up a little bit and take another look at our gain formula, or our delta V. We know that that's equal to V out over V in. We can derive V out and VI in and put that in terms of IC times RC in parallel with RL, and IB times the equivalent resistance at the base, which is RE plus R prime E brought across the beta barrier. So we're multiplying by a factor of beta plus 1. Now if we take IB and multiply that by the beta plus 1, we get the IE, and we know that IC over IE is alpha, and it's pretty close to 1. It should be pretty close to 1. Also, we generally know that R prime E is kind of a small number, so we can then say that delta V is approximately equal to RC in parallel with RL divided by RE. So that RC in parallel with RL divided by RE gives us the gain at midband. So now if we come back to where we were at and we're looking at the circuit in terms of high frequency cutoff, we need to now factor in the X sub C total at that frequency. And we know that at cutoff, X sub C should be equal to that resistance RC in parallel with RL. We also know that the X sub C is at a negative 90 degrees. So if we bring those together, we get something that's equivalent to 0.707 times the original resistance. Those two in parallel will be equal to 0.707 times that original resistance. So we can see that our gain, our numerator, has gone down by a factor of 0.707, and that our gain is going to go down by a factor of 0.707. And if we take the dB formula and run that into the dB formula, we can see that 20 log of 0.707 is equal to minus 3 dB. And we know that that's where we should be at the cutoff frequency, minus 3 dB. So we know that at FC high, our gain, our delta V is down by 0.707, or we're at 70.7%. We're also at the minus 3 dB mark. So is there a way for us to bump that gain back up? I mean, we know that that capacitor in parallel with the load is going to just keep sucking that number down as frequency goes up. So what can we do to prevent that or extend our bandwidth by extending our frequency high cutoff? And so one way of looking at it, it might not look like there's much we can do with the numerator. It's got the C total out in parallel with RC in parallel with RL, and as frequency goes up, that X sub C is just going to keep on going down. But there might be something we can do in the denominator, or something more obvious we could do in the denominator with RE. So if we could bring RE down in the denominator at the same rate that the numerator is falling, we would be able to essentially, whatever is, as it's coming down, it's factoring back out, keeping our delta V or our voltage gain the same. And that's what emitter peaking is attempting to do. So if we want the denominator to essentially degrade or decline at the same rate as the numerator in our voltage gain formula, we need to find a capacitance that goes in parallel with RE that is resonant at the same frequency, at the same FC high. That's what's happening in the numerator. And so here I've got the formulas to kind of calculate out what that capacitance would be. So now with the emitter peaking capacitor calculated for and put into the circuit, we know that at the FC high, it'll look like this formula. So we'd have 0.707 times the parallel resistance in the numerator and 0.77 times the RE in the denominator, and that gets us right back. So the 0.707s cancel, and we end up back with our RC in parallel with RL over RE. Now both the numerator and the denominator have the same roll-off rate of 20 dB per decade. They're both rolling off at the same rate, so whatever that number is as it rolls off, they are going to factor out to a point. At some point, that capacitance on the output is just going to start acting like a short to ground and run our signal straight to ground, and we're going to lose our response. But this should extend out our bandwidth, and certainly at our cutoff, our current high frequency cutoff, it'll bump us back up 3 dB. As you can see, the 0.707s cancel and it returns us back to our 0 dB point with our original voltage gain. So here is a sketch of our high frequency side of our Bode plot. You can see in black we've got our original circuit and our original FC high marked at the 3 dB point. Now when we put in the emitter peaking, we know that the 3 dB point, the original FC high, the gain returned back to basically our 0 dB point. So we know that that frequency shifted up 3 dB to the 0 dB point. So does it make sense then that the original 6 dB point on the original curve, if the 3 dB point shifted up 3 dB, would the 6 dB point also shift up 3 dB and therefore become the new frequency high cutoff point? All right, so here is the math to determine any frequency at a specific dB on the high side of the Bode plot, the high frequency side of the Bode plot. So the formula is the gain in dB is equal to 20 log of 1 divided by the square root of the quantity 1 plus the quantity of frequency, some frequency, divided by the cutoff frequency squared. And what that is telling us is we can figure this all out because everything has the same roll off. So we know that everything rolls off 20 dB per decade. So that's where this formula comes from. So if I want to find the frequency at 6 dB down, I can put this formula in terms of minus 6 dB and start working the formula. I've got all the math here showing in terms of frequency and cutoff. And then finally at the bottom, all the way at the bottom, if you want to step all the way through this, we get that frequency at minus 6 dB is equal to 1.727 times the original cutoff frequency. Okay, so because everything shifted up 3 dB with the emitter peaking capacitor, we can now say that our new FC high with the emitter peaking capacitor should be pretty close to 1.727 times the old cutoff frequency. Now sometimes this is referred to as the K or improvement factor. So we've improved our bandwidth by a factor of 1.727. Or you could also say with emitter peaking, we've got a 73% increase in bandwidth.